Why hello lovely humans, Jen Foxbot here. Welcome to part 2 of probability. Yeah! Alright, so in this example we are going to look at a more complex example of discrete probability, aka things that we can count with our hands or our brains. And we're going to look at more formal definitions of the terms that are used in probability, including quantum mechanics. So, in the previous video, we talked about pulling candy out of a bag, very important, and we discovered that the probability of finding some object equals the number of those objects divided by the total number of objects in your bag. So for example, the number of Twix divided by the total pieces of candy would give you the probability of finding a Twix in the bag at random. In this case, we're going to look at rainfall. Yay! So let's say you measured the amount of rain each month for an entire year, and then you plotted the data so that you can figure out how likely is it going to rain this month and how much rain is it probably going to have. So actually, that's what pretty much every city does. They measure the amount of rain in a given month, and then they gather historical data so that we can make predictions about the future. Super important. I need to know how much I need to water my plants and what my outfits are going to look like in a given month. So this is what Seattle's data looks like for 2019. So in 2019, for example, there was 1 month where there was between 0 and 1 inches of rain. So in that case, we have rainfall kind of, I call them bins. So instead of saying like it's exactly 1, it's going to be between 0 and 1, then between 1 and 2. Okay, and so we have on the horizontal axis, we have the amount of rainfall. And then on the vertical axis, we have the number of months that saw that amount of rainfall. So we can ask very similar questions that we did about the bag of candy, plus a little bit more. So the first thing that we need to do is, well, calculate the total number of months. And hopefully we all know that it's not the Gregorian calendar. The calendar that we use, which I'm forgetting its name, has 12 months. And so the total number of things that we are dealing with are 12. And if you wanted to count by hand, you could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Boom, done. We have 12. Okay, so now we can ask, for example, what is the probability that it's going to rain less than 1 inch in a given month? So probability of less than 1 inch would be just 1 out of 12 because there's only 1 month that had less than 1 inch of rain, and this is about 8.3%. We can also ask, what is the most probable? Just like we did previously. So most prob for most probable. And by looking at the graph, we're like, oh, boom! Between 1 and 2 inches was the most likely amount of rain. So the probability of getting between 1 and 2 inches is 5 out of 12. Because there were 5 months that had between 1 and 2 inches of rain. So that's going to give me 42%. The meaning of life? I don't know. Okay, so then we can also ask different things like what is the median of our data set? So the median, you can also think about it like the middle of your data set. And the reason why it was hard to do for the candy is because the median would kind of depend on how we arranged our data. If it was alphabetical or if it was increasing smallest to largest, it would give us different results for the median. But in this case, since we're plotting rainfall in inches, we probably wouldn't order our data set any differently. So in this case, the middle of our data set is going to be the halfway point where we have 6 months that had more rainfall and 6 months that had less rainfall. I'm going to just do this by hand because we have a small data set and it'll be easier for you to see. So if I count 1, 2, 3, 4, 5, 6, I end up in this bin right here. And then just to double check that I have 6 larger, we have 1, 2, 3, 4, 5, 6 larger. So the median of our data set is going to be between 2 and 3 inches. Pretty cool, right? Okay, and now we can calculate the average or the mean of our data set. So this is going to be really, really important in quantum mechanics. The average of this data set is going to be the sum of each of these quantities times how frequently it occurs. And since at this point I can't really deal with the ranges, I'm just gonna round up a little bit and say that this bin kind of represents 1 and below. This is 2 and below, and I'll just write it out. Okay, so we have 1 month where it rained less than 1 inch, which I'm just going to represent with 1 inch, and then we just add up all of the other bins together. So then we have 5 times 2 inches plus 4 times 4 inches plus 1 times 5 inches and plus 1 times 8 inches. And then you divide that by the total number of months. So divided by 12, and this is going to give me 3.3 inches. So a quick aside, the reason why I'm doing this is just because I plotted in bins. A more accurate way to do this would just be to go back to the actual data set and then say, count up the number of months, count up the average rainfall and then just divide by 12. But it'll probably give you something close to that. So let's write this equation in a more general form. Yay, general form! So then we can apply it to all the things. Okay, so let's see here. We are going to say that this is going to be our symbol for the mean of our data set. And in quantum mechanics, it's called the expectation value. And so it's going to be this little J with wings on it or brackets around it. And so the expectation value of a particular thing in our data set, which is represented by J, is going to be the sum of that particular thing times the total number of times that it occurs divided by the total number of things. And so you'll notice that this nj divided by n total, oh boom, that's just the probability of that particular thing occurring. So then this equals the sum times j, oh, I'm gonna run out of space, so I'm just going to erase that and save myself some space, times the probability of that thing occurring. And you're like, wait, what just happened? Okay, so j basically is the amount of rainfall in inches. So in this case, you could say it's 1 inch, 2 inches, 4 inches, 5 inches, 8 inches, and I'm rounding up. Okay, so this is a very important term. And the really important thing to know is that both the median and the mean, or the expectation value, don't have to actually occur in your data set. And that can be really confusing because if you say the mean of our data set is this number, but that number doesn't ever show up in your data set, you're like, but wait, how is that the mean? It's different than the most probable. So mean and most probable are not always going to be the same thing. In this case, in our data set, the most probable is between 1 and 2 inches, but our mean is going to be over here. And that's often how it goes. So hopefully that made sense. Let me know if you have any questions on that. The next thing that I want to talk about is that your data sets are going to look different, but sometimes they might be giving you the same average value, which could be very confusing. So let's say that we have two graphs. Oh, that's funky. Let's say that we have 2 graphs that look like this. Well, this one looks like this, where we have 4 of one particular example, and then over here we only have 2, and then we have, it spreads out like that. So in this case, the total number of things that are on our graph are the same. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we have 6 little boxes and the same middle value, or the same most probable value. Not median. Actually, well, yes, they are both the median, but most probable is really important. So these 2 graphs are very different, right? Because in this case, our most probable value is a lot more probable than either of these values. And in this case, it's slightly more probable. And another way to think about it is that in this case, our data is very narrow, and in this case, our data is very wide. Another way to say that is that the spread of the data in this graph is large, and the spread of the data in this graph is very, very small. It's like if you took a piece of toast and you spread peanut butter all over the middle, and you're like, the spread is very narrow. And then in this case, you spread it all the way out, and you're like, the spread is very large. It's pretty much the same thing. Pretty much. Okay, so now we need a quantity to be able to tell us if our data is very spread out or if it's very narrow. So I want to save this somewhere. Well, okay, I'm just going to define it for you. So the expectation value, that's the expectation value. This is called the variance, and it's represented by the Greek letter sigma, which is kind of like a sideways 6. So the variance, which is sigma squared, that's the variance, is defined to be hold on, let me make sure I get this right. The average, the expectation value squared minus the square of the averages. Okay, that is real crooked. So I'm gonna say that again as I write it again because it probably requires a second definition. Okay, so it is the square, the average is, wait, hold on. The average of the squares minus the square of the averages. Okay, the easiest way to think about it is just to look at it. So to give us some more space. So this value, j squared within our tiny little bracket wings, equals the sum of j squared times the probability of that value versus the square of the averages is where you just figure out what the standard average of your data set is, and then you square it. So in this case, you square j and plug it into this equation to find the average of the squares, because it's in the little wings, yay! And then in this case, you just do this standard equation and then you square the result after. Okay, cool. So, in general, this quantity is going to be larger than this one. Cool. If you end up getting 0, then it means that your data set looks like this. Boop. Done. There is no spread. Everything is the same. That's boring. That's a boring data set. The real world very rarely, if never, looks like that. So, this is the variance. Sigma by itself. Oh, whoops. I messed up. Boom. Yes. So this is the standard deviation. So then sigma squared is going to be j squared minus j and outside squared. So my bad. So this is the standard deviation, just regular old sigma. And sigma squared is the variance. So you would not use the square root sign. I got confused because I'm used to mostly doing the standard deviation. I almost never do the variance. But it's important to know the distinction and to know the right labels. Okay, so hopefully I didn't confuse you too much there. Let me know if you have any questions about what we covered here. I ran through it pretty quick, so I'm happy to answer any questions you might have or provide more resources if you need. Cool, thank you for watching. Check out part 3 where we will dive into continuous variables. Yay! Bye!